Okay, the economic analysis framework basically is a very straightforward cash flow, discounted cash flow. I'm assuming that you've done that at least sometime in your lives. You did DCF, or discounted cash flow analysis. For World Bank projects, we use a discount rate, which is the opportunity cost of capital you can think of of 12%. That is fairly standard across all World Bank projects. Not all development partners use 12%. I can tell you EIB uses 5%, EBRD uses 10% or thereabouts. And there are arguments as to why we use such a high rate of 12%, which is actually high. The European Union or European Commission uses 3%, typically. The argument that we as a World Bank use is we want to really maximize benefits of the few dollars that we have. So in a way, it's some form of capital rationing. Okay, so we will allocate funds to those projects that have the highest returns. So if you cannot show a positive return at 12%, there are other projects in the world that do have 12%. So that's why I call it capital rationing of some sort. But the very principles of discounted cash flow analysis, you apply a discount factor derived from your 12% discount rate. Now, the key thing with roads, and this is quite different from other infrastructure projects, is benefits are not estimated directly. Benefits are derived. Benefits are derived by comparing a without project case, which is our base case, usually the current road. So let's say, think of the East-West Highway before it is constructed to 4 lanes. Think of a section, let's say, what has not been done now, somewhere from Zestafoni to Kutaisi. Still 2 lanes, right? So that's our existing road, 2 lanes, and the plan is to construct it to 4 lanes. Okay? Normally, we would go well beyond 10 years. Okay, so usually we would go to 30 or even 40 years, but you have the issue of diminishing returns. After 40 years, it's, with a discount rate of 12%, you're pretty close to zero. And so the cutoff point is usually about 25 years when, because of such a high discount rate, after about 25 years, then anything beyond that has a almost zero present value. Okay? So the without project is the existing case. We estimate what are the current operation and maintenance costs for the existing road. 2-lane existing road, what are the costs of operation and maintenance? What are the costs of vehicle operation? I will define what we call this VOC, vehicle operation costs. And these are in $1 million cumulative per year for each year. These streams are undiscounted. Okay, so the total transport cost is basically the operation and maintenance cost plus the vehicle operating costs. Now, this is a very simplified discounted cash flow analysis, just to illustrate the point. Then we would have the total costs, and then we apply the discount factor, we multiply that by this, and you get that. Okay. So, as you can see, that decreases with time, even though the vehicle operating costs and the transport costs may be increasing in future because we applied such a high discount factor, then this is decreasing. Nevertheless, the total of the two is your present value of costs estimated for your without project case. We do the same for the with project, so we're going to construct, assume this is per kilometer, okay? The costs look very low. So assume this is per kilometer, 5.8 million investment per kilometer to widen the road to 4 lanes from Zestafoni to Kutaisi. Of course, this is a fake case, but don't take these as the unit costs you would get on Zestophony to Taiti. But nevertheless, because you're constructing a new road, your operation and maintenance costs will be lower. So if you look across here, it will be lower, but you have a high construction cost. Okay. Initial cost, capital expenditure, 5.8 million, let's say per kilometer. Then your VOCs are expected to reduce thereafter. And that's the whole point. We're trying to, the reason we build a road is to reduce the costs of vehicles and users traveling on the road. So your VOCs will reduce. Now the total of these three columns is your total transport cost for the with project alternative. Again, you apply the discount factor, multiply that by this, and you should get this column here. And the present value after 10 years is 20.3. So our net present value is basically the difference between that and that. So at 12%, when you subtract this from that, you get 3.557. Okay? So that's how it works in roads. And of course, the economic rate of return by definition is the discount rate at which this would be zero. Okay? So to calculate that, you have in Excel, you have a function that does, but in practice, you just iterate. Okay? Clever algorithms for coming to that. But here it shows a economic rate of return of 29%, which basically means that if we had used a discount factor, a discount rate of up to 29%, we would still have a positive rate of return. So that is how it's done. Now the issue is, how do you get to estimate these costs and benefits? I forgot that I have this graph that demonstrates how you get to the 29%. You basically increase your discount rate. Well, since it's positive, we didn't need to go below 12. So we could have just gone up and up and up until you get to the point where you cross this NPV equal to 0 line. But you've done all of that. That's the simple part. Now we begin to get into the actual meat of the subject, the actual estimation of costs. For roads, the costs are basically capital costs from construction, which is your land acquisition, equipment, labor, management, and overheads. And then the maintenance costs, the type of maintenance that you do, the physical costs, and then of course the management costs as well. Benefits, as you've seen from the table before, we estimate the reduction in vehicle operating costs, which is the difference between the without project and the with project case. Okay? That's the reduction in vehicle operating costs. What I didn't show in the table were other costs, like reduction in travel time. Okay? If you put a value of time, let's say at the moment it takes 1 hour to travel from Zestophony to Kutaisi. Make it easy. Okay? Once you construct it to 4 lanes, it will be reduced to say 40 minutes. So you're saving 20 minutes. What is the value of time of the average passenger? And how many of those passengers are there? Okay? In a year. Okay, so that adds to the benefits from travel time savings. Then you have changes in road maintenance costs, which usually, depending on what you do, if you're widening the road, the first 10 years the maintenance costs may be low, but after that it may be higher. But because you're discounting, it will still come up as a benefit. And then accident rates, which unfortunately in Georgia is quite high. How many people are killed at the moment on the 2-lane road per year, and what is the value of life? I assume, Eric, that these very basic fundamental economics principles have been done by your students. So you know the concept of estimating value of life and so on. Okay? So, assuming that by increasing to 4 lanes, 2 in each direction, you actually reduce the rate of accidents. Not always true, because people tend to travel faster, and sometimes accidents actually increase. But in theory, you should go down in the number of people killed, because you're separating the direction of travel, and also if you have proper driver education and so on, then the accidents should go down as well. So you have another set of savings. Now, these are from what we would call the normal growth of traffic. The fact that you improve a road can generate increased demand for travel. So at the moment, if traffic is growing at, say, 2%, and then you improve the road, it might start growing at 5%. So the difference between 2 and 5, the 3% extra traffic, is what we will call generated traffic. That is increased demand, which the benefits from that are calculated separately from normal traffic. You also have other benefits like changes in the values of goods moved. So a typical example would be at the moment, because the road is in such poor condition. I'm going to give a really stupid example, okay, so you understand what the issue is. Because the road is in such poor condition, people may decide to, let's say, fly some goods. Okay, say it would be a stupid example, just to give you the concept. Because A, it takes too long at the moment to travel on the road, and B, the road is such poor condition that if you have fragile equipment, you wouldn't really want to risk using the road. Okay? So with an improved road, you probably get higher value goods being moved. So that is also a change in the benefits, and that is also derived benefits or generated benefits. You have increased agricultural output. Typical example, the farmers or the industries along the road are now able to reach markets at a greater distance, and therefore they're able to produce more. Okay? Those are some of the derived benefits and other social benefits as well. We will, of course, stick to the simpler things to do, but I'll describe them. The externalities are probably traffic noise, vehicle emissions will increase. If you can apply a cost to this, then you can include them in the analytical framework. And energy consumption, we can include that as well, but for this lecture, I'm not really going to go into some of these externalities. So the modeling framework, as I showed in that table, which showed only 10 years, we would normally model or calculate, predict costs from anywhere between 10 to 40 years. The typical average is 25 years. Okay. I say typical average because from an engineering perspective, roads are normally designed with a life of about 25 years. The road pavement is designed with a life of about 25 years. After 25 years, you need to reconstruct or rebuild. It depends on the type of road pavement, but typically 25 to 40 years is typical.
In Israel, we still have some Roman roads, you know?
Do you know why? This is a very interesting discussion, but do you know why?
They didn't hire this hunter then.
Could be. Or they just didn't think about cost benefits. In those days, it wasn't a question of cost.
So, built really well.
You build it regardless of the cost. You build it to last. And if you can build it to last forever, even the Saudi Arabia king now would not dream of building a pyramid because the cost would be incredibly high. And nobody in Saudi Arabia would support any king that tried to build a pyramid as his, what do they call it, esophagus or something, where to be buried, okay? So in other words, the philosophy those days was different. These days we stress cost-benefit analysis as the basis for building infrastructure. Those days it wasn't. You just built it to last. So that's the reason, I think. I'm not really an expert on
Egyptian
roads and other things. Okay, so we've done the modeling framework is basically, as we said at the beginning, you compare the with project against without. You predict the traffic for both cases. You analyze alternatives, and then you compare the predicted costs. So basically, that's what we're going to be doing. We have a computer program, which is called HDM, that does all of this. You provide the input data. It then predicts the road deterioration. It predicts the roadworks, the maintenance, the repairs, and so on. It also predicts the vehicle operating costs, the time costs, accident costs, and then does your table, the table I started with, and based on that, it discounts those annual costs to get your NPVs and internal rates of return. So let's start with road deterioration. I like this because it actually demonstrates what happens with the road. You start off in a new condition. At some point it will be ideal, and then it goes to poor condition. Over time, of course, over time and traffic. The same thing happens. You may have a different road, a different pavement, but it's still the same thing. You have new condition. At some stage after construction, it's in ideal condition. Eventually, it deteriorates to poor condition. So that is effectively what these models or equations built into the computer model do. You have a road that starts off in good condition. Let's say condition is measured in terms of riding quality. A low riding quality means it's in good condition. As you apply traffic with time, riding quality gets poorer and poorer. Note, as you go up, it gets poorer. And at some point, you would apply some maintenance standard, which would then bring it maybe not back to the same level, but improve the condition over a fairly short period of time. We're talking here, the x-axis is probably 25 years or 40 years, 25 to 40 years. So this would be done within the rehabilitation or reconstruction. It would be a matter of 1 year or something, okay? And then we continue again. So typical pictures of what we do. This is what we call a gravel road or unsealed road, where it starts off fairly good condition, and if you go to the remote areas of Georgia, you'll find some of these types of roads that don't have a paved surface. Okay, and here we're measuring the riding quality. We have a concrete pavement, cement concrete, I should say, which again this is fairly new, but over time will deteriorate. Or a bituminous pavement or bitumen. A typical road in Tbilisi will be something like this, and we calculate how many potholes you'll get, how many cracks, loss of materials, etc., etc. Okay, so there are computer models that predict how a road pavement is going to deteriorate with time, and of course there are different types of pavements. As I said, over time, even if you do maintenance, you will get some deterioration on the surface of the pavement. And this is a picture that shows not the same road, but a typical condition getting worse and worse until you get to something that is really broken. Again, I'm sure you've seen some of this around. I like to include, actually this one was from, guess where, which city? Washington DC. So don't be embarrassed if I give examples of Tbilisi. You do have this even in the capital of the richest country in the world. Maybe it's not the richest anymore, but this one is from Brazil, from Rio. It's one of the streets in Rio de Janeiro. But essentially, what is happening is to try to calculate what will happen to a road after it's constructed. You apply traffic, there is time, there is the impacts of climate, the weather and so on, so it will deteriorate over time. I like to include a joke as well, once in a while. This is, of course, a fake picture. Nobody would go fishing in a pothole. But, so, what are these models or equations that are used to predict road deterioration? This is a typical extract from a typical equation, which is going to predict how fast a road will crack, and so on. You don't need to know what these coefficients are, but
Well, we do want to
we'll need a whole year to do that. But effectively, these are econometric models. Okay, so we apply, we observe what has happened in the past, and then we do some form of regression analysis to come up with these coefficients. Okay? And that the coefficients are basically different types of roads, the loading factor, the strength of the pavement, and the maintenance history, and so on and so forth. So if you wanted to do some high-powered econometric analysis, this is the type of thing you end up doing. Roadworks would have the opposite effect to deterioration, as you might expect. If you apply maintenance, then you slow down the rate of deterioration. Here we're measuring deterioration in terms of riding quality, of something called roughness, which is actually a technical measure of road condition. The higher it is, the poorer the road condition. So high IRI, if you maintain your drainage, you seal your cracks, the road will deteriorate slower than if you don't do any maintenance. And if you don't do any crack sealing at all, then it's going to deteriorate faster and faster. That's basically what this graph is showing. But the equation that was used was the one I showed earlier. Now, those were the costs of maintaining a road. We also need to estimate then the benefits to road users. Typical road user costs are vehicle operating costs, time costs, and accident costs. VOC is basically your fuel, oil, tires, vehicle maintenance, the depreciation and utilization, and of course any interest on capital for purchasing the vehicle or any parts. Again, there are equations that we use, econometric models, equations that will tell you that depending on your road condition, good to poor, measured in terms of riding quality, a heavy truck will have a cost dollars per vehicle kilometers, which will be much higher than, say, a car. So your traffic is actually composed of several percentages of cars, utility trucks, buses, heavy trucks, and so on and so forth. So the average, weighted average vehicle operating cost will be in proportion to the percentage of the traffic mix. But the econometric models are separate for each type of vehicle. In some countries, you have rickshaws, which are really motorcycles that carry either passengers or freight. Not very common in Georgia, but very common in India, Pakistan, or at least the Far East. So you have these equations that will not only model the vehicle operating, but also model the impacts of congestion. I think you all know what congestion is. You've driven it to Tbilisi. When you have too much, when the flow exceeds capacity, vehicles slow down, so you burn a lot of fuel, which is an operating cost for the vehicles. Okay? So again, there are equations for predicting the impact of flow volume on the overall throughput and therefore increasing cost. Okay, so the effect of, again, another set of econometric models for calculating fuel consumption as a function of speed. As I said, as you have high congestion, speeds reduce, say less than 20 kilometers per hour. You're burning a lot of fuel, but you're not really going far.
What is the difference between the Caribbean, Kenya, and India?
First of all, different types of vehicles. Okay. In India, the vehicle mix would be more the rickshaws and so on. In Kenya, for example, there are no rickshaws, and the trucks are different. India's vehicles are probably the least efficient. I don't know if you've been to India, you'll see they have these very old trucks with very inefficient engines. So that's the difference, really, is the type of vehicles. I don't want to say anything about the driver behavior because that also contributes something, but there is also some element of driver behavior. Again, the typical econometric models for calculating the different components of vehicle operating costs. Accidents, unfortunate, but they do happen. What you estimate is the rate of accident depending on the type of road that the vehicles are using. And then you apply different cost values depending on how many people are killed, the value of life, how many are injured, and those damage to vehicles. So again, you apply a cost factor depending on the predicted rate of accidents. Costs that are, shall I say, intangibles or externalities are mainly emissions, energy consumption, energy dissipation, never energy loss, but dissipation. These impose a cost on society, for example, health costs. Vehicle emissions, particulates that have impact. Lead, I think we all know, has a negative impact on health. So these are costs that are imposed on society, but are not necessarily always calculated or included in the estimation. Energy balance, how much energy is lost, and so on and so forth. So I'm going to skip a lot of those and just go straight to how we use cost-benefit analysis in roads. The most typical application, of course, is for new projects, new construction. The example I gave of Zesafoni to Kutaisi, where you're going to construct a new road effectively. That is a typical project cost-benefit analysis. So you look at typically a new construction or upgrading. Upgrading is simply an existing road that you either widen. New construction is obvious, it's a new road altogether. What we do calculate is the net present value, the economic rate of return, and some other economic indicators, benefit cost ratio, first year rate of return. And we do a sensitivity analysis. Okay. A sensitivity analysis, okay, I've given a different example here, Agara to Zemo Siauri. The base case, the net present value calculated was 26.7 with an economic internal rate of return of 17.5%. Now, the sensitivity analysis, what would happen if our costs increased by 20%, everything else remained equal? Your rate of return would fall, but still greater than 12%. Because remember, the discount rate, 12% is the cutoff point. The other negative scenario is if our traffic was reduced by 20%, again your rate of return would reduce from 17 to 15, but still greater than 12%. The combination of the two, the rate of return would fall to 13.6. In other words, we reduce our traffic by 20% and we increase our capital expenditure, capital cost by 20%. This particular road section will still be viable. So we would say that this particular road project is robust. It remains viable, economically viable, even under extreme scenarios of increased cost and reduced traffic.
What is the status in this particular stretch?
Under construction.
Under construction.
Yes. Okay, we do similar things for other infrastructure projects. Obviously, the modeling is different. You don't have vehicle operating costs for power transmission projects. The benefits are from improved reliability, and we have mechanism for estimating the benefits from that. Lower domestic cost of supply and lower regional cost of supply. So when we add these and add the subtract the two, we should get something discounted, of course. This is now discounted at 12%. You get a net benefit of 3.2. With an economic rate of return 13.6. Sensitivity analysis, same sort of thing we apply. You can see here, assuming we increase our costs by 10, 20, 30%, or we reduce our volume of power transmitted by 5, 10, 20%, what will be the impact on the economic rate of return? In the base case, where no change, 0 and 0, will be 13.6. Okay, same. And then we see here what happens if we simply increase our costs by 10%, then our rate of return will fall to 11.6. If we reduce our volume of power transmitted by 5%, that falls to 12% without increasing costs. And if you do a combination of the two, of course, this is what you get. Okay? So sensitivity analysis, in the same way as we did for roads, we would do for other infrastructure projects. In this particular case, we would say that this project remains robust up to a reduction of 10% in transmitted power and an increase of about 10% in cost, but not both. If you do both, then you fall below 12%, significantly below 12%. Let's say the roads department is preparing an investment program for the next 5 years. Which roads in Georgia should be included in this investment program? So basically, what you're doing is for each road section, section, you do the same analysis, maybe over 20 years, and you estimate the economic benefits. And from that, you rank which of these projects should be included, as long as they have a positive rate of return, positive NPV, and a rate of return greater than 12%. And they would be included in the program, and what you're doing, the first year program would be above that line, second year program there, and third year program and so on. So effectively, you're taking a whole network of roads, and then you're prioritizing which road sections should be included in this year's investment program, next year's investment program, and so on.
Sorry, is that then solely on the basis of the economic rate of return?
This is solely on the basis of economic rate of return. But I think I get to the question you're asking. Are there other factors that should influence prioritization?
I would imagine some strategic objectives or something like that.
Political.
Yeah, I don't want to say that.
Voters, yeah.
The reality is yes. but the theory says you shouldn't, because these other types of prioritization factors, you would be doing what we call a multi-criteria analysis. You're including other factors beyond economic return. Okay? If you set out to do so and openly tell the public that this is how we will prioritize, we will include factors beyond economics, then it's fine. What is usually not fine is to put factors that are not out in the public. For example, roads that lead to the governor's home or the president's home, where there is only 2 vehicles a day, the president leaving his house and coming back to his governor, not president, or whatever, okay? So those kinds of prioritization would not be acceptable. However, if you have a community in a remote part of Georgia where there's not enough traffic, but they would otherwise be cut off, then that is a fair factor to include, provided it's in the public domain. That's the key factor. But what would happen in those cases, you would not obviously build a 4-lane road, but you would apply some minimum standards to keep the road open throughout the year.
One question. When you decide the ranking, do you take into account also the interaction, for example, that it would be with the rehabilitation of one road with another road? So the model includes this type of feedback?
Yes. Actually, that's done in the next round, where we do what is called a network strategy. And that looks at the interaction between roads that are within a region or within a country or within a province or within a city. And you look at the interaction between the roads. And here, it's more of a, I'll use the American phrase, ball gazing. Okay? We want to see beyond the next 5 years. We want to see 10, 15 years what will happen to a network. We want to be able to say to the government, you should be budgeting X million dollars per year for your road network, either for maintenance or for improvement of the road network. A typical example I give here is, again, these figures look extremely low, $10 million. Let's say this is just Tbilisi. Even 10 million for Tbilisi is too long. Take a small city or small town in Georgia.
Rustavi.
Which one?
Rustavi.
Okay, Rustavi. Okay, Rustavi. We talked about riding quality or average roughness being measured. The higher it goes, the poorer the condition. So if your city, Rustavi, was budgeting only $10 million for maintaining its road network, then the model will show that over 10 years, the entire road network will get worse and worse. So what this is saying is, if you want to keep your road network at the current average condition, you need to be budgeting about $15 million per year. But if you want to improve, and your target is to improve to say something around 3.5, again, IRI is a measure of riding quality, you don't need to worry about it for the time being. The key thing is the trend in the graph is improving. The riding quality is improving. Then you need something of the order of $20 million per year. Of course, I did this analysis in some time back, the year 2000. We need to add maybe 15 now to this, but the concept is the same. Okay, so that's the end of it. That's basically how road economic analysis works.